In the name of Allah, the most gracious, the most merciful. You saw, ladies and gentlemen, when I was talking about the topic of tube rating, the chart and the cooling chart, there are certain things that you must ask about when you buy any machine. And among the very important things is the modulation transfer function, which expresses the machine's ability. In resolution. What does resolution mean? It means that I have something called special resolution, meaning that the machine can see two small objects as if they are two distinct small objects. What do you also want to say? Well, I just drew a line. So we have two lines and each line has a gap next to it. I have two line pairs and each line has a gap, so I called it a line pair. Now, how many line pairs do I have? Two line pairs. All right, I will take 1 centimeter and draw in that 1 centimeter. Line 2, 3, 4. So, how many line pairs per centimeter do I have? 4 line pairs per centimeter. That's clear and nice. So, I came here. 4 line beer. I drew the same centimeter, but instead of putting 4, I put 7. So now I have 7 line pairs per centimeter, but it's still the same centimeter, or I got the same centimeter and put it. Let's say this is 20 line pairs per cm, right? Now let's say in the first case you can see 4 line pairs per cm with your eyes. Can you see 4? Or is there a problem? At 7 line pairs per cm, you can still see them clearly, even though the space between each lion bear has started to decrease. This means your resolution must be good enough to distinguish between 2 lion bears in order to see 7 lion bears. But what if I increase the lion bears to 20 or 30 or even 40? Let's say 30 or 40. More, and more, and even more. We see the largest number of line pairs per centimeter, which represents the resolution of the machine. It needs to see whether the number of line pairs per centimeter is large or small. It's important to have a high resolution, unlike, for example, SD or regular X-ray. If the machine can see the largest number of line pairs per centimeter, this indicates that the machine is good and its resolution efficiency is high. This is related in some cases to the modulation transfer function. If I now draw line pairs, they are very close to each other, but my machine cannot see that they are a group of lines. For example, there are currently 1, 2, 3, 4, 5, 6, 7 line pairs per centime. But my machine's efficiency is low. But my machine has low efficiency, so it can't discriminate between these line pairs. It will see them as if they are one line, like this, right? It perceives them as one line because it can't see them as two objects that are very close together. The machine cannot discriminate between them. It will see them as if they are one object or two objects. Okay, but in reality, they are indeed, in fact, 7-line pairs, not just one line pair, right? All right. So then, actually, the real contrast is this. Real contrast. This is real contrast. It indeed has contrast, meaning these line pairs are indeed present with a difference between each line. There are actually 7 distinct line pairs. However, my machine is not able to distinguish them clearly enough. So I have real contrast, which is essentially the input I have, the actual image, the truly real one. Then I possess this perceived output of contrast as well, because these 7 lines are perceived as just one single line, while in reality, complete and full-fledged, genuine contrasts exist here. Apologies once again, but yes, there really exists such thing called absolute 100% pure unadulterated contrasting elements within it all right now. How much exactly out a whole 100 percentage points could possibly be seen through my own device? Ratio concerning said element always remains situated down below inside denominator section, wherefrom machines will eventually produce their respective outputs. The ratio to the contrast, which is the input I provide, is the modulation transfer function. Its value is always higher than the output, right? Or am I wrong? The real contrast is always 100%. There is a difference on this among doctors, but the output of the imaging machine is either going to match the input or be less. It will never exceed it. That's impossible. So here, the contrast that the machine will produce will either be 100 or less. This means that my modulation transfer function, which is the output contrast relative to the input contrast, is always capped at 100%. Now, the output contrast is what I need to calculate. When I calculate it, I will derive the value of the modulation transfer function. But how do you calculate this contrast? Let me explain how this contrast is derived. If I have this black point object like this, like this, like this, like this, I said, by God, I want to take a line profile. What does line profile mean? It means I will take a line and say how much intensity each point on this line has. Let's assume this is an X-ray image, and you have photographed, for example, a coin. The coin will appear in what color? The white is correct, and it will be high intensity for the background. The background will be black, and the coin itself will have high intensity. I said I want to take a line profile. What is a line profile? It means I want to see the value of intensity at every point along the background. As it passes over my object, I found that this part I can call black, meaning it dropped a bit until I reached the area of the object where I find the intensity started to rise, reaching the maximum at the center of the object, and then it dropped again, right? So this curve is called the line spread function. The line spread function, or what I do in the way I call it line profile, means that I took a line and looked at each point. Each point in my image has a certain value. Now, if this curve, I hope you all are not confused. Here is the image, and here is the object. Next to the object, there is another object. I took the line profile. What will it do? It will look like this, right? Am I wrong? As long as I can see the space between the two peaks, I can make a discrimination, right? I can differentiate between the two objects. Great. Now here is one object, and here is another object. Take the line profile. Ha 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 ha. The spirit function gives me an indication of the contrast or the resolution of the machine's performance. So what am I going to do now? I want to test this machine. What is its modulation transfer function? Is it 100%, 10%, 20%, or 30%? The highest is 100%. So what should I do? I will take something at 100%. What is the highest? 100%. So what should I do? What? For example, a phantom is like a square object, and this phantom contains groups of line pairs. For instance, I might say there are 5 line pairs per centimeter, and then create another group that reduces the spaces between the line pairs, thereby increasing the number to, let's say, 5 line pairs per centimeter directly. I will tell this group 10 line pairs per centimeter, and I will say increase it. For example, I will tell this group 15 line pairs per centimeter, and I will tell this group 20 line pairs per centimeter, 15 line pairs per centimeter. Centimeter. The more you increase the number of line pairs per cm, the more you increase the number of line pairs, which means you reduce the spaces between line pairs. If you want to test the resolution of your machine, you need to check whether the machine can see 5 line pairs or not. So, what do you do to find out if it can see them? You perform the line profile that we mentioned. The line profile will show up in the 5 line pairs, so you can see it or not see it. If you come in the 10, you will take the line profile and you will still be able to differentiate. When you reach 15, you find that the spaces between the peaks have started to decrease, meaning your curve, instead of being differentiated like this, could look something like this. As for 20, it might look like this. I can't really tell. It establishes a relationship between line pairs and the value of the modulation transfer function, MTF, with a maximum output and input value of 100%. The value of the modulation transfer function, MTF contrast. The highest value is 1, which is 100%. The input is like the output, right? You find that the more the number of lines per centimeter increases, what happens to the machine's ability? Does it decrease or increase? It decreases. So the number of lines per centimeter increases, and the machine's ability to resolve or differentiate between the lines will decrease. Therefore, the curve goes down. And that's why the highest point here is 100%, which is the real value, just like what appears in the image. Now, what about this area? This area represents a low number of lines, and when we tried to increase it, the machine couldn't see it anymore, so it went down. So, here we have the machine's ability to see. Now if I came to tell you that I have this and that, and I have this is machine 1, and this is machine 2, and this is machine 3. All right? So I have the first machine, which is A, the second machine is B, and the third machine is C. Let's assume that they all start from 1, which is 100%. So, who do you think is the machine that can see the highest number of lines efficiently? C, because you took an example here. Let's say 20 lines. The curve indicates the resolution of the machines. I can see how many line pairs per centimeter. Do you think if I have a mammography machine, I should choose C, B, or what? This is the point, because here the MTF curve is crucial for me to see the largest number of line pairs per centimeter possible. That's why, for example, in the CT, it tells you that the CT can see 20 line pairs per centimeter, while the mammography machine can reach up to 20 line pairs per millimeter, not per centimeter. Can you imagine the difference in the number of line pairs? The more the machine can see, the standard you have to judge it by is 10% efficiency. I look at the 10% and see how many line pairs the machine can see. For example, it saw 20. In B, it saw more than in C, and so on. So you see at a certain value, the 10% at A saw, for example, 10 line pairs. Of course, B saw 20, and C saw how many? It saw 25. So 10% is the standard modulation transfer function. 10% is the standard modulation transfer function. Right. This is what allows you to see how many line pairs per centimeter. Okay, doctors? I would have been very upset if the internet had gone down. But thank God it didn't. This is the curve that you see, the modulation transfer function. And these are the different systems A, B, and C. Here are the line pairs. For example, here you have 3 line pairs in this area, which is the largest number of line pairs. This image is not very clear about what I was talking about. But here you have 1 line pair, and here it starts with 3. The more you increase the number of line pairs per cm, the more you test whether your system can see. But it's not more complicated than that. The idea of calculating it mathematically, I don't think it will be difficult, because it relates to the line profile and the line spread function and how to convert it to the metric value. There is something detective quantum efficiency that shows how well a system can convert an X-ray input signal to a useful output image. Detection is low. How do you feel? You feel the same. How do you feel? You feel the same. It feels the same, turning the X-ray input signal to a useful output image. What I really want to say is that I edited a few things. The effect that can take this dose and create a conceptual impact is the conceptual effect itself. The more it can do this and has a greater conceptual impact, the better it can achieve this. The conceptual effect of The X-ray photon is that it allows me to have a better image. This is the conceptual effect. So what does it express? It expresses the effect between the signal to noise ratio for the output, which is derived from the signal to noise ratio squared, is based on the input. You will always find that the signal to noise ratio is the same concept as the detector I was talking about earlier. In reality, the signal to noise ratio of a real image should be at its highest, meaning your SMR, which is the signal produced when you calculate the ratio between it and the noise present in reality, should ideally be the highest. However, the output, or what comes out, will always be less than the actual value, similar to the concept of the detector, and the contrast of the output and input follows the same idea. You will indeed find that this detective quantum efficiency has specific values that actually depend on the particular type of imaging plate itself. If this imaging plate is used in high-resolution technology, use it in the high-resolution technique, you will find that the detective quantum efficiency is 0.12, as you can see. But why is the standard 0.25? That's my standard. And why is it 0.12 in high resolution? The value decreased. Because in the simple area, you need a signal to noise ratio. So when you play around with the resolution, the detector or detective quantum efficiency is not related to the resolution. But what is it related to? It's the ratio between the two that calculates it for you. But it expresses the efficiency of the counting itself, or the efficiency of the detection itself. For example, if you have two imaging plates, one standard and one high resolution, the high resolution is like one standard and one high resolution. The high resolution is already set. This is a standard imaging plate, and this is a high-resolution imaging plate. You will find that the phosphor layer is thick in the standard imaging plate, while in the high-resolution imaging plate, it is thinner. The crystal size here is larger, and in the high-resolution imaging plate, it is smaller. So what does this mean? It means that your detection quantum efficiency is higher in the standard imaging plate. Why? Because it is thick. What does that mean? It means that your efficiency is higher in the standard imaging plate. Therefore, the area exposed to radiation is higher because the crystal size is larger, which also increases the area exposed to radiation, thus enhancing the detection efficiency. In contrast, the high-resolution imaging plate has a thinner layer and a smaller crystal size, which reduces the exposed area, improving the resolution. Instead, in summary, unlike when you are detecting a wide area, you cannot differentiate or determine exactly where your signal or radiation is coming from. However, at this point, you become more accurate and more resilient. The thinner layer has the same idea. It will reduce detection efficiency, yes, but it will give you a higher signal, or a higher signal to noise ratio, right? The detection quantum efficiency refers to the efficiency of the machine to detect radiation, or the process of detecting radiation. Excuse me, doctor, but is the image blast the same as the sector? Yes, it is the same as the cassette, which is considered the crystal. In computed radiographic imaging? Yes, it is computed radiographic. Yes, in the computer there is imaging with the imaging plate and the cassette, and their crystal has the same crystal and phosphor of the crystal. It has heavy technology and a new crystal, and it has 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 a type of thickness, depending on the type of technique that can be used for imaging. You will find that what is used in mammography is different from what is used in general radiography. For example, if there is a computed radiographic CR system here and another CR system there, and both are undergoing readings, you will notice that the cassette used here is different from the cassette used there. Right. If you please, can you write whether the detection quantum efficiency is higher in the standard imaging plate or in the high-resolution imaging plate? It is higher in the standard. Why? Because the detection in this case is higher? Are you talking about detection? The detection is higher. May God help us, but the detection is higher. This value expresses the amount of detection coming in. But the signal-to-noise ratio, let me explain it to you so you don't misunderstand. What does signal-to-noise ratio mean? It refers to the relationship between the signal coming from an object and the background, right? So when I say, for example, sometimes when I give you an example, have you seen C images? Surely, right. So if we look at the dose in pediatric cases, how does the image appear to you? No, the city image from Egypt doesn't feel right.